customer slash, provider perspective. He was the customer, I was on the provider side. He can really give a good tongue lashing, I could say, and then really make it sound like he just, complimented my wife or something. It's really good. So he also has a distinction of having an alter ego. I won't say at which con. Maybe you can figure it out on where he's from.
Spent on security.
So he has an alter ego that,
I'm also the grok.
That he presents with, but he's not going to present us with that today. But I can tell you that if you know him from that, it's probably the worst kept secret in InfoSec. And maybe if you're nice to him, he'll let you in on the joke. So I give you Paul Melson.
Ladies and gentlemen, Bill Blanham. Oh, thank you, man. Always awesome to be back here in Augusta. BSidesAugusta is definitely a go-to. So if you're watching this at home on YouTube, next year, 2017, you need to be here. I still can't believe they let me speak, quite frankly. I'm Paul Melson. I do cyber stuff for Target. I've been there about 18 months, and I have I have 4 hobbies, kind of in order. My kids, we foster dogs for an assistance program. I collect beer, and I collect malware. Unfortunately for you, I'm only going to talk about the last one. So this talk is a little bit about automating malware analysis for threat intelligence. But before we really get into how that all works and before we tempt fate with some demos, I want to talk about why it is that we analyze malware in the first place. I think it's an important thing to kind of baseline from, right? So malware analysis, if we go back to like the antivirus days, is actually one of the oldest practices in information security. Chances are pretty good that most of you in the room work somewhere where they had antivirus long before they had internet connectivity and a firewall. But what's interesting is that viruses started out as kind of self-replicating, destructive, frankly pointless tools, but now they are monetized. They are just that, tools for the commission of crimes of various types. So when we're doing malware analysis, what we're really doing, right, fundamentally, is we're going back and we're trying to understand the capabilities of the binaries that we're running into. And by understanding those specific capabilities, we're hoping that perhaps we can infer the intent of the adversary, right? At the end of the day, there's an attacker who's trying to do something, almost always monetize something in some way or gain some sort of an advantage, whether that's direct compensation for what they've done or whether it is some sort of tactical or intelligence advantage. The malware is just a means to an end. And understanding the malware maybe lets us understand what that end is. And so that lets me pivot very nicely into the Lockheed Martin kill chain. So we had a spirited conversation over drinks last night with some of the other industry luminaries that are here at this conference. And so whether you're a fan of MITRE or Lockheed or the Mandiant attack lifecycle, they're all valid. But my point in bringing this up is at the end of the day, every attack has to go through phases in order for the adversary to get to the end. And so by looking at malware analysis, right, we get to interact, or we have the opportunity to interact. We don't always see it, and we aren't always there and present in the IR cycle, but we have that opportunity to interact starting at delivery. But when we're analyzing malware, and one of the reasons that we want to automate analyzing malware is to get faster at this, because the point of the malware is it will almost always tell us something about the installation and command and control. Right, that initial payload, that dropper, whether it's a macro in a document, whether it is a primary stage 1 loader that delivers a secondary mission payload, or whether it's a handoff bot, right? There's an entire industry in the crimeware family where they're dropping rats specifically for the purpose of selling access to your network to someone else. Somebody else buys it, they use their rat to drop the new malware, and then they exit the scene and the new adversary is in your environment without ever having to figure out how to hack you in the first place. And the thing about this is if we can quickly move from delivery stage to understanding installation and command and control, because those are things that come with the delivery of the payload, right? By working through that, then we have the opportunity to disrupt the actions and objectives of the adversary. So the speed at which we move may give us the opportunity to get ahead of the adversary, and really ultimately this is the value of operating with, pick your model, but with some level of attack model in mind. So a little bit about my research. I collected data using virus total intelligence. I like VTI because it has an API. I did some reverse engineering on a couple families of malware. I picked new POS things and neutrino. So this is neutrino with a 3, not neutrino the exploit kit, also called Cazadet by some of the vendors. And the reason that I picked these is that they're widely prevalent, and they have a kind of an understood end, right? One of the functions of neutrino is, now neutrino does a few things. It can act as a DDoS bot and some other stuff. It also has credit card RAM scraping capability, which of course is new POS things, bread and butter. So I definitely have an interest in malware that does these things. So we track a lot of that. And the goal was to do some reversing on these, understand them, build some Yara signatures, deploy those Yara signatures into VirusTotal for hunting, and then when VirusTotal found me new samples, automate the pull down of those and triage into a Viper framework. So Viper, if you're not familiar, is a static analysis framework put together by Nex and Kev Breen, and it's a community group brought to you mostly by folks that have worked also on Cuckoo Sandbox. So this is the static analysis, cousin to Cuckoo's dynamic analysis. And actually they have a pretty slick integration. So I'm going to be showing you this because this is just kind of my favorite tool set to do reversing with, and it's handy because it has an API, so it makes automation really, really easy for people who are not natural born developers like myself. So let's dig in on neutrino, some of the stuff that neutrino does. So here's these are snippets from IDA, some screenshots just to prove to you that I know what I'm talking about when I write these Yana rules. So here we've got some strings that get created. These are variables that are designed to capture track 1 and track 2. If you're familiar at all with mag stripes and credit cards and the way that those work, track 1 and track 2 are written data structures. Traditional mag stripe reader connected to a PC will just pull those into an import buffer, usually the keyboard buffer, and simply make those, it's essentially like somebody typed them in, and those will be just sitting resident in one of the input registers for the process that has hooked that device. So track 1 and track 2 are, it kind of calls out exactly what the malware is getting ready to do. This is some interesting stuff about neutrino as well. So if you look at all the little red bubbles there, you'll see things like maltest, tequila boom boom, sandbox, virus, malware, sample, virus, sandbox. And so first giveaway of the talk is, who can tell me what tequila boom boom is? That is exactly correct. So Tequila Boom Boom is the sandbox and user ID that VirusTotal sandbox is in. So if you see binaries that contain the string Tequila Boom Boom, they're thinking about VirusTotal. The cool part about that is that you can totally use that against them, right? VM detection in binaries is usually a sign of bad stuff. And one final thing about neutrino is that it statically builds command and control in. So command and control can be flipped by the panel, but in a lot of cases, and in fact in most cases where we're talking about crimeware, the builder will simply import the command and control structure directly into the file itself, right? So if you have the PE binary, you have the command and control data in front of you, you just have to know where to look. And in neutrino, it actually stores it in a base 64 encoded string that's just extractable by strings. So it's some really, really basic. There's no fancy obfuscation here. It's just enough so that you don't immediately go, hey, that's a funny looking URL when you go look at it. So, but sure enough, if you decode that, you get the URL of the panel. The panel can move the botnets to new panels, but they have to be talking to it at the time. And all the C2 for neutrino is over HTTP. So we've completed reversing. Here's some Yana rules. One that's the one on your right is strings-based. So we leverage Tequila Boom Boom along with some of the other bot commands in the C2, along with some of the URL parameters that we know that different versions of neutrino tend to use. On my right, your left, you can see the sandbox evasion opcodes are broken out there. That's not exactly human readable, but trust me, that's not a bad rule either. I don't have network. This is perhaps my sole complaint about BSidesAugusta is you're going to have to take my word for it that the hunting script runs just fine in my sandbox every 5 minutes. So there's my cron tab, and then at the bottom you can see the VTI notification script, which I'll show you the code in a little bit. Be gentle. I'm not a developer. You can see it reaching out, talking to VirusTotal and saying, "Hey, what do you have for me? Hey, I have these two rule hits for you." And then what the code does is it checks in with the Viper repo and says, "Hey, do you have this hash?" And in this case, it's saying, "Yes, I have that hash." So we take no additional steps. If the Viper repo says, "No, I don't have that hash," then we pull the file down from VirusTotal, insert it into Viper, and then have Viper triage it using the same Yana rules again, and I have it do a few other things like tag it with import hash and if there are any packers that are identified in the file, and a few other interesting tricks that you can do with Yana and store-t in Viper. So, and then here's proof that I did in fact ingest this file into my Viper repo. So you'll see the hash matches, and it is in fact tagged and ready for me to go ahead and analyze it at my leisure. So let's do this. Okay. So this is the aforementioned terrible Python code that makes up the my VirusTotal hunting script. It's primarily based on requests in JSON and a little bit of regex because not everything does JSON as well as JSON should be done. So here we build a list of rules. So this is the list of rules. This corresponds to the hunting rules I have deployed at VirusTotal. I have a substring or a subroutine here that just generates the import hash value using the Viper API. We reach out, pull notifications. If we have any notifications, we kind of come through and extract the ID, the hashes, the rule set name, the type. Check and make sure that what we're looking at is an EXE or a DLL. This is a lesson hard learned if you're going to use automated hunting functions to pull binaries from whether, regardless of whose source you use, this applies whether you're using VirusTotal, Malshare, or any of the other available repos out there to pull samples. You definitely want to make sure that you're pulling down valid Windows executable files if that's what you're looking for. Otherwise, you will just end up with a file system full of other detection companies' detection. Hack if you are so inclined. If you need McAfee signature updates, you can get them off VirusTotal. And everybody else's stuff too, frankly. Okay, so then we check, make sure it's a file that we actually want. We check in with the repo and say, hey, do you already have this hash? If it has the hash, then we just skip it. If it doesn't have the hash, then we go ahead and pull the file down from VirusTotal and then store it, and then come back here and upload the file via the Viper API. And so this is sitting, I've got a little T2 micro instance sitting out in Amazon EC2 that does.
Hi folks, Angie here. Unfortunately, we had a little video freeze up, so we lose the speaker's motion and audio until about the 15-minute, 52-second mark.
So I have written a few things here. Some of the stuff actually calls back out to VirusTotal to pick up some additional information. I won't be able to demo that, but I have this guy here. So one thing I've done, right, so this is the corpus of new POS things. There are 85 samples in my repo, and this is all based on using tags. I have a little bit more neutrino than I have new POS things, but they're all kind of useful. And just showing off again another module for so new POS things. I showed you encode C2 in base 64 string, so I just wrote a little string search that looks for base 64 string patterns using a basic regex. If it finds it, takes that string, tries to decode it. If the decode is successful, it gives me the value. But that is like super helpful when you're trying to get C2 from a whole bunch of samples. So let's do that. So this screen down here, this is the Viper API console, just to show you that I'm not cheating. And this is the demo version of the report. And so what I can do is just tell it, hey, I want everything that's tagged a particular way. So in this case, I want everything that's tagged as neutrino, and it's just going to go in there and start generating this big, ugly, pipe delimited mess of stuff that I can then do later analysis on. So you can see we're ripping out all kinds of stuff. User agent strings, import hashes, compile times, file size, all different kinds of things to just sort of get, here's the set of indicators that I think I might want about this stuff. I'm going to take a minute to talk about this approach versus metadata collection in a big data environment, right? It is also a viable approach to take and rip all of this metadata as you collect the samples right off of your source and put it into an Elasticsearch environment. And that will give you lots of things because, so something like Viper keeps all of the malware samples in what I would call a zoo live on disk. That lets me write new code and go back and reanalyze those over and over and over as I learn new things. The problem is scale on that end, but the challenge, but you give up the ability to continually reanalyze samples if you move to metadata collection in a big data environment. So I guess, in short, what I'm saying is do both. All right, so now that you've watched this grind for a minute, let me show you one other. So I did some kind of discrete ones for some specific use cases. Because so each one kind of, I had to know a little bit about how to do the extraction, right? So either, most of these it's some variation on strings and decoding to get the command and control out. There are a couple that I'm not going to show off here that are, rely heavily on opcodes, which they're super slow because you have to. I have yet to find an elegant way to not have to just iterate over a bunch of different address spaces inside of the sample to actually get the C2 out. But this one should work. There we go. So, and you can see it's starting to rip things out. And all the way to the right there, you'll see it start to parse out the command and control. And this is all, caveat, right? This is all live. I hope nobody is trying to browse to any of these sites. Most of this is old and down, but as we get to the bottom, there's stuff that is up as of this past weekend. So, I'm doing this all on a closed network on a machine that I'm going to reimage when I get back to Minnesota, but anytime you're playing with live malware, do so at your own risk. And don't just consider the safety of the machine or the network that you're on. I mentioned earlier I run all this stuff in Amazon. I do not do any of this on the work network. That's how you get your laptop contained by Blue Team. But if you will look up here with me, you will see that there are some really good reasons not to just automatically deploy all the indicators that you extract from malware. So that is legit a sample of neutrino that somebody has actually configured the email spam relay functionality in the config. So I found that they have a Yahoo account. They're using a Yahoo account to deliver spam for this bot net. So neutrino, by the way, is kind of like the scumbag starter kit. It's all the documentation is Russian. It is total skitty land. If you get into looking into this particular family of malware, it's kind of hilarious, some of the stuff that ends up happening. Somewhere up here, I think if we look hard enough, we'll see. I thought I had a sample that was there we go, 192.168.71.2. So for those of you working on threat intel feeds, this is from the Special Insider threat version of the intel feed. So this is why we don't automatically deploy indicators. This is the part of the problem I haven't figured out how to solve quite yet, frankly. Perhaps there's a blacklisting or a protecting thing that you want to do, and you're willing to kind of take the risk of the gray space in between to say, here are the top 500 or so domains that we know we just have to whitelist, and we would never want to deploy an indicator against just because it'll just be too darn noisy. And these are the IP ranges that we would never want to deploy an indicator against because, again, it'll be too darn noisy. But short of that, I really don't have a better approach other than I would say this is exactly the kind of stuff that when we pull it all together, we want to send it right over to a team of Intel analysts who can, one, help us dedupe it out of their indicator repo, and two, determine which of these indicators are actually valuable indicators. And being able to pass that to them with the full context of things like an extracted malware config is a huge help.
What if you took the registration date of those domains and added that as a piece of information?
So the question is, what if I added the registration date of those domains and used that as a piece of data? So yeah, bulk scraping. Okay, so a funny story about. Well, here, let me pause on your question and come back to it because I've got a slide that will kind of talk to pieces of that, right? So because part of this is absolutely about let's unmask the bad guys. So this is output of a slightly different run of the script I literally just showed you. And so what you can see here is, so I just pulled out, that's the SHA-256 hash value of the file, the compile time from the PE header. So if you're not familiar with Windows PE headers, they capture a bunch of information like the import table, whether or not it's a x64 or x86 architecture instruction set, and they also include a UTC or an epoch time timestamp for the compile time of the file itself. And so what's interesting about that is that when I started collecting compile time specifically because what I wanted to do was build a campaign timeline to say, hey, this was built at this time and deployed. Now, it is trivial to upset that and rewrite that data, but I completely failed to predict how common time stomping on PE compile time is. But that's not bad news, it turns out. So in this case, though, let's take a look. So down here you can see 1992, 06, 19. I think we can all agree that that was, in fact, not compiled on DOS 4.01. I don't even think the PE standard had been ratified at this point in time. So that's clearly a garbage date. And that ties to this C2. But that C2 ties to the other two samples immediately above it. But that is literally to the second the same bogus date as that timestamp up there, which is tied to that C2, and that C2 connects it back to those two samples. And what's really interesting is if you look at the compile timestamps on those two others, those are only a few minutes apart. And I propose to you that this is a pattern, a behavioral pattern of a human being who does a couple of test runs with Visual Studio and uploads those to VirusTotal. And then shortly thereafter, uploads a time-stomped version of their malware to VirusTotal for checking, and then deploys the time-stomped version. because we can find the timestamp version uploaded a whole lot more times. Moreover, what I suggest to you is that because that pattern repeats, I now have the ability to connect that C2 and that C2 to a single operator. Does anybody want to argue with me or disagree with me on that? So, and even if that's not correct, that's a really interesting coincidence, and coincidences are great. Because coincidences happen a lot, it turns out, when people automate things. So this is across that neutrino data set I just showed you. And so I knew, right, like, so down here on the left, you've got 1970-01-01, midnight January 1st, 1970, which is all zeros on epoch time. So like, that's like the laziest time stomping you can do. I just smoked it. Like, it's just gone. Now, I can't be the only person who's mad that Windows will run something with this as a compile time timestamp. But you can see we've got these two from ancient times down here on your far right. But as we move down, what are the chances that on July 9th, 2015, at 10:09 p.m. and 31 seconds, 62 different Russian scumbags compiled the same kit and deployed it? So this is a statistical anomaly. There's no way that is a legit timestamp, right? Now, if I'm looking at a single atomic sample of this malware and I see that timestamp, I'm probably going to skip right over it, because July 2015, this was totally a highly usable, very much viable, very active piece of malware. But 62 times, and I'm still pulling new samples with that timestamp. So it seems really, really unlikely that this is coincidence. So what that means, though, is I think I have 62 samples, or roughly a third of the samples of neutrino that I've been able to capture from VirusTotal, all attributable to one person. And I don't know what that is. Maybe it's like his kid's birthday, or the day he bought his Porsche Cayenne, or whatever Russian cyber gangsters drive. So I took this a step further, though, and I said there have to be, it's cool to be able to do this, but not everything punches you in the face quite as bad as this one does. So what other patterns can we identify? And so I started taking multiple. So if you're familiar with node graphs or force relationship or social network analysis, SNA. So this is not technically a social network, but the same algorithms totally apply, right? So what we do is we create a couple of connection types. In this case, compile time values and C2 values, and then look for all the connections between. So the blue dots are binaries, and the lines making up all those pretty little constellations are the different relationships. So the blue lines are compile time, and the green lines are C2. And so right off the bat, you notice there are two really big clusters. You don't have to be Martin Holstein to be able to figure out that those are probably related. But there's some pretty stuff that gets drawn in here too. Like this constellation here is really kind of an interesting one, because you remember this screen here. That is an expanded view of that. And what we find falls out when we overlay this again is that there's actually a third campaign that's tied into this same pattern. Now, I did nothing to prep this data. This is literally just they have the same values. Show me all the relationships where the values are connected, and this falls right out. See data analytics. So this is new POS things. And I wanted to use two different variants because what I didn't want to do was just assume that this tactic could work, and then if I got lucky, it would work, and then I could never apply it to anything else ever again. And it turns out that this bore fruit over here as well. This one is compile time and impash. So I'm dropping C2 completely from the new POS things conversation, and instead we're just looking at import hash. An import hash, right, is a representation of the import table, like all the function calls that the builder loads when the binary first executes. And when we zoom in, so this one that's down here, bottom left, when we zoom in on that, what you can see is a whole bunch of different compile times in the blue lines that go around the outside. But all of the import hashes are the same across all of these samples. But what's really interesting is then up in this cluster in the upper left for you is, or excuse me, upper right for you, that's same import hash, same compile time. Well, again, so now you've got time stomping. So these are all the same. I'm going to, my hypothesis is what I'm looking at is that is a single builder for new POS things, and the upper right quadrant is a single actor who likes that timestamp a lot. So neutrino, again, compile time in C2 clusters, you can see right off the bat there's a couple that are very, very tightly combined. But there's some interesting stuff too if we kind of look out to the periphery of this graph. And so I took the raw extracts that I showed you I generated earlier, I threw these in Kumu with basic social network analysis algorithm and outputted these pretty pictures. And so when you really drill in on these, this time you're looking kind of upper right on that graph, out along the edge, you'll see there's 4 kind of grouped together. And this is them, and we found the affinity across 2 different C2s, all using the same time stomping. But what's really cool is we picked up this outlier too, which I posit. So the actor, he or she, time stomped this to all zeros, right? Some basic stuff. But I posit that they screwed up and let one get away that they hadn't cleaned up the PE header to their own satisfaction. And in fact, we are now able to date these 2 campaigns to June of 2015, right? Because the bad guys screw up. So now I'm going to pivot back to John's question about, have we ever looked at all of the who is data behind them? So if you are in IR detection or threat intel, I got to put a plug-in for domain tools, or at least the capability that domain tools provides to do domain history. Because the ability to take a domain and see all of the IPs and the original registrant data, because a lot of stuff gets kind of picked up and swept away and cleaned up, and that's fantastic. There's a whole group of miscreant punchers out there who find bad stuff and get it taken offline, and that's fantastic because for most of the organizations out there, they can use all the help they can get. But for those of us that are interested in unmasking the bad guys, it's really cool to have the original registration data too. And long story short, yes, and it's very interesting because just like they make these mistakes from time to time, they make registration mistakes. So lots of this stuff gets registered through GoDaddy or I forget the one Inu or whatever the one is that's in Enum. Thank you. Yep, the one that's the one that's in South America anyway, or Central America, Panama. It's in Panama. And so, and all their stuff gets blinded. Every once in a while, they screw up, and their real details come through. There's a neutrino actor, and I'm fairly certain I have his apartment address in Vietnam. I don't want to put it up on slides and put it out on the internet in case I'm wrong, because I might be wrong. But it kind of looks like this if you look through the data, right? You have all this stuff that's just overwritten and anonymized, but they do this so much. Some of these folks iterate through it clearly so often, right? That they put out a campaign gets burned, put out a new campaign, right? Just redeploy the toolkit. So and every once in a while they're going to screw up, and when you catch them screwing up, you tie that data back to all of the other commonalities that you have about the rest of the campaign that they're running, and now all of a sudden we can start to build a picture of who's actually behind this stuff. Intel. So, and then again, just more stupid Kumu tricks. This time, impassion size clusters, and you see we keep basically the same shapes from here to here. So the thing you can. So I've dug deep on these. Those two are competing versions of the builder kit for neutrino. Almost none of the neutrino that you see out there has been highly customized by anybody that can code their way out of a wet paper bag. Most of it's kids that just run the builder script. Literally they have a nice little Visual Basic GUI that you can set up the config, run it, and compile it, and deploy it. So, and then the panel is all PHP and MySQL, and I'm sure probably also not the best at handling inputs, but I don't know anything about that. So other TTPs as we look through this, right? So I pulled I used domains and IPs for the C2 piece, but the thing about URL-based C2 is that domains and IPs is only part of it. So this is a bit of an eye chart, and I apologize for that. But you'll see I pulled this out into Google Docs and threw this up and highlighted some stuff where these patterns repeat, right? So at the top you'll see those are the same three domains with /fonts tasks, /images tasks, and /js tasks.php. A pattern that also repeats down here in the blue, and then we find an orange one where I think we have more of a complete picture because we get JS, images, and fonts, and we also get CGI and ink. Does anybody else see it though? Right, so now I can tie those three domains together. Does anybody see the fourth? It's right there. The pattern doesn't repeat for that domain. I don't have complete data, but font/tasks.php occurs in all three of the other ones. So now, just by looking at the naming convention that this person seems to prefer, because people are creatures of habits, we can tie all four of these campaigns back to probably the same person sitting in the same room in the same city, possibly somewhere in Vietnam. So just for fun, this is Funsies. I decided to take all of my data and throw it at Kumu, and after it stopped whining, I got this picture. And so you totally can't read that, but what this shows, right? So your upper left and lower right. So upper left is new POS things. Lower right is neutrino. I think, anyway, I label it in a minute. Yes, I was right. And in the middle, 1992, 06, 19, wait, what? So I was super excited for like 5 minutes. Where I went, holy crap, I found somebody changing malware families just by luck. Actually, I didn't. Super excited. And I do show you this to show that it's possible that if that is what I had snagged, that it would be possible to draw some of those conclusions. But thanks to a blog post that Hexacorn wrote in 2014, my hopes were dashed. It turns out that 1992, 06, 19 compile time date, because I thought to myself, I really need to run this to ground. It turns out that this is a Delphi compiler bug. And initially I was like, oh, that sucks. And it does mean that I probably can't tie a single actor to two variants of this thing. But that is still a useful piece of intelligence to understand that that is a Delphi compiler bug, because what it tells me is, one, I have somebody using both variants of this malware, or multiple actors potentially, using the same variant, or multiple variants of malware, using this old version of Delphi to compile code on Windows. Additionally, I did some research and discovered that that's a thing that malware authors like to do because it screws up some other stuff and makes it a little bit harder for antivirus engines to detect when it's built with Delphi. So now all of a sudden, I have a compile time signature that if, let's say I've got, bro files running in my network, scraping PE file data out and putting it into a data set, I might be able to find something that was compiled with Delphi, which is probably not a lot of the commercial software that I run, and certainly not a lot of the new software that my devs and team are downloading onto our network, but might be malware. So, interesting data nonetheless, though not as cool as I initially thought. So, closing thoughts. So one, automating both the hunting of particular threat tools and analysis of the data they contain is absolutely plausible. Using clustering of static indicators to find relationships can definitely reveal the presence of an individual because their habits, patterns, and mistakes fall out in that data. And finally, there are seemingly endless possibilities for pivoting, right? I just picked kind of 4 things, but we could have gone on user agent string. We could have gone on, we could have gone on different packer types. There's all sorts of different things that we could have pivoted on as we were looking at this data and potentially found more and interesting relationships between the actors, right? So this is, I feel like I've just kind of scratched the surface on this approach to working from binaries all the way back to actual bad guys. So, and with that, I want to take a quick second to, so I, like anyone in the field, am blessed to stand on the shoulders of some giants and leverage work of those that have come before me. So they probably don't even know how much they helped me with this, but Alan, Wyatt, and Nick Hoffman all contributed significantly to my work, and I want to make sure that they get credit for helping bring some of this into existence. So thank you to you guys. All right, and I don't know if I've got time for questions or if I just got to get to the giveaways, man.
Maybe how about one question and then giveaway?
Okay. Any questions?
With the impact value, I've had trouble using that before because things like .NET and AutoIt have identical for every single file ever generated.
That is absolutely correct. Import hash has some challenges based on the builder. So I totally agree with you. .NET using identical import hash makes it not a great individual indicator. And so again, right, indicator selection when you're doing this kind of analysis is sort of important. If I were working with a family that was primarily .NET, I would have dropped that because it just wouldn't have been a differentiator. In this case, they weren't .NET, so it had some value, but yeah, that's absolutely a piece of it. Is I go back to the earlier part of the presentation where I was talking about really getting to know the malware you're hunting by doing some reverse engineering and understanding that. And you definitely want to bring that context and those learnings all the way with you into staging your analysis. All right. What's that? Giveaways? All right. Okay. I got to think of... Okay, what language is the neutrino documentation written in?
Russian.
That's correct. It was written in Russian. All right, and Lockheed or Python? All right. All right. One more.
The compiler bug, what language was?
Oh, yeah, so the 1992 compiler bug, what compiler has the bug? Shut up first. Right.
Oh, don't give him anything.
Okay.
No.
Thanks, Bill. I just do what Bill says. All right. Thank you very much.
Thank you, Paul. That was awesome.